All right, so let's answer this question. What's the probability of getting 60 or more heads if I flip 100 coins? And remember, how we're going to answer this question is we're going to approximate this probability with simulation, with computer code. We're going to figure out how to do one experiment. That means in this situation, flipping 100 coins. We're going to run the experiment a bunch of times. We're going to flip those 100 coins over and over and over again. And then we'll find the fraction of times where the number of heads was at least 60. All right, so how do we run the experiment once? That's the first step in this process. We've already seen how to do this. It's with NumPy random choice. So we use NumPy random choice to flip the coin 100 times. So I'm going to use choice. Here I'm going to use with replacement, which is the default. I'm going to do this 100 times. If I do this, I get an array of 100 coin flips. Okay, so I flipped a coin 100 times. If I do this again, run this cell again, I'm going to get a different result. I mean, you can check and see that it's different, but it is. Okay, so heads, heads, tails, tails, and so forth. So I get a different result every time I run this piece of code. Now what I want to do is I want to calculate the number of heads. Okay, so that's the result of one experiment, is how many heads were there. So I'm going to calculate how many heads do I see here. And to do that, I can use NumPy count non-zero. NumPy count non-zero is a new function that counts how many entries are true. It takes in an array and counts how many of them are, how many entries in the array are not zero. The way we usually use it is we pass it in an array of trues and falses, and it counts how many entries of the array are true. So in this situation, I want to calculate the number of entries of coins, which are heads. Now, if I compare coins double equals heads as a string, I get a Boolean array back. And then I'm going to pass this into NumPy count non-zero, and it's going to calculate how many trues are in that array. Okay, so let's test it out. NumPy count non-zero. It'll tell me there are 52. So if I run this over and over again, I'm going to get a different number of heads every time. As we'd expect, the number of heads is usually about 50. If I flip 100 coins, the coin is fair. The average number of heads should be about 50. But there's some fluctuation because this is random. So here I saw 52 heads. Now I see less than 50. I see 45, 52. Now if I keep running this, eventually I'm going to see one that's greater than or equal to 60, but it doesn't seem super likely. There was 58. I saw one before, 61. I'm about to give up. 5, 4, 3, 2, 1. Okay, I'm done. As we can tell here, it's not very likely. But if we keep running this a bunch of times, maybe in a for loop, then we'll see eventually some of them will be greater than or equal to 60. And then if we run this 10,000 times and see 100 times we see greater than or equal to 60, we take 100 over 10,000 and get that probability. So to make this easier, we're going to take our experiment and put it into a function. Okay, we don't have to do this, but this makes things nicer. So I'm going to take the code that I just wrote, okay, NumPy random choice, count non-zero, put it in a function with no arguments. I don't need any arguments for this one, and return, remember to return the number of heads. So I put it into a function. I run this function once, it gives me the number of heads. Run it again, gives me another number of heads, and so forth. Okay, so this kind of wrapped up the experiment, put it into a function, kind of made it easier to work with. Okay. So now that I've written the code to do my experiment, I'm going to run the experiment over and over and over again. Remember, that's the next step. Okay, so as I already mentioned, the way that we can do things over and over and over again is with iteration, with a for loop. So I'm going to use a for loop. Inside my for loop, I'm going to run my experiment, and I'm going to keep track of the answers. So this cell right here has some code that we're going to be writing over and over and over again the rest of the quarter. This is the basic framework for an experiment. Okay, so you'll see here I have a for loop. In the for loop, I'm iterating for a certain number of repetitions. So here I'm saying let's run this experiment 10,000 times. Okay, so 10,000 times. I'm saying for I in NumPy A range, so I'm going to run this 10,000 times here in repetitions times. I'm going to run my coin experiment, save the result to a variable called head count, and then append head count to an array called head counts, which I created up here. So that's the basic formula. I create an empty array, then I for loop, and append the result of my experiment to the empty array, which is no longer empty after the first iteration. And then after I run this cell, which will take just a fraction of a second to run through 10,000 experiments here, I have an array, head counts, of the result of every experiment. So that's kind of cool. I mean, I flipped 100 coins 10,000 times in a fraction of a second using code. Here is the result of each. I had 42 heads, then 50, then 46, and so forth. I want to know what fraction of the time was the result 60 or greater. And to answer that, I can use NumPy count non-zero. So I take my array of results, head counts, I compare it to 60. Okay, so where were the head counts greater than or equal to 60? Throw that into count non-zero, and I see 274. Okay, so 274 times I saw 60 or more heads. I want to calculate the probability. So what proportion of the time did I see at least 60? So that's 274 over the total number of experiments, 10,000. So I write at least 60, that's 274, divided by the number of repetitions, and I get 0.0274. Okay, so the probability here, remember 1 is 100%, so the probability is 2.74%, approximately. If I run this again, you'll notice I get 268, which gives me 0.0268. Run this again, I get 2.63. I'm always around 2.6, 2.7%. That might be accurate enough for me, or it may not, and I would need to run more repetitions, maybe 100,000, which would take 10 times as long. So let's take a look at the distribution of the outcomes. In other words, instead of just looking at 60, right, that how many times was the outcome 60? I want to see how many times was the outcome 50, how many times was the outcome 52, and so forth. And to do this, the right tool is a histogram. It's the distribution of the results. Okay, it gives us more information than just that number of how many times was it greater than or equal to 60. So I'll just make a data frame here. So I make an empty data frame like this. We've seen this only once or twice so far. So this creates an empty data frame. I'm going to add a column to the data frame called number of heads, and that'll be the head counts array that I created on the previous slide. Then I'll plot a histogram. I'll set the bins so that the display is nice, and then I will make it a density histogram. Here's what we get. Okay, so let's interpret this histogram a little bit, because we're going to be using histograms like this in the rest of the quarter quite frequently. So it's important to understand what we're seeing here. So what happened? I ran my experiment 10,000 times. Every time I got a number back. That number was the number of heads in that experiment. And what this is showing is the distribution of those results. So how likely was it that I saw, the result being 50? So in this case, you can see that the most common result was actually not 50, but maybe, 50, 51, maybe like 52 or 53. This bar here is actually the highest. But, that's just due to some random chance. The peak clearly is at or around 50, which is what we would expect. If you run this experiment over and over again, you don't expect 55 to be any more likely than 45. There's some symmetry here. Okay, so we see that the probability of getting something greater than or equal to 60, right, which is looking here. So you look at 60, and then all of the outcomes which are greater than or equal to 60 are these. That would be the area of this part. If you add up the area of all of these bars, You're going to get 1. Okay, because this is a density histogram, it's normalized. So the area of a bar in this histogram is the probability of seeing a result in that bin. Okay, it's approximate because these are approximate probabilities, but it is a probability. Okay, so we can calculate the area of this, the region here, if we can even draw a line here. Okay, the area of the histogram of the blue bars right of the red line is about 2.6 or 2.7%. That's what we calculated on the previous slide, but we can see it again here.